Before we get started, questions over the homework. What we're doing today is continuing solving. We're continuing going through solving these logarithmic equations. Now, just like the note sheet we went over Thursday, we do need one term on either side, especially if we have numbers or expressions outside of the logarithm. So we have two logs on one side, number on the other. So we need to be able to rewrite this, or we need to rewrite log of 2x plus log of x minus 5 as a single log. And we can actually use the product property, which says that log base b of m times n is equal to log base b of m plus log base b of n. So if we have two things multiplied together inside a logarithm, we can rewrite them as a sum of those logs. Conversely, if we have two logs with the same base being added together, we can rewrite it as a single log with what's inside each of those logarithms being multiplied together. So we can rewrite these two logs as log of 2x times x minus 5. Questions on this here? And really, that was the big step for this, is that we rewrote the sum of those two logs as a log with what's inside being multiplied together. Now, the rest of the steps follow exactly as we had on Thursday. Since we have variables inside the logs, we need to put both sides to the base of whatever the base of the log is. And since this log's base is not written, it's understood to be 10. So we're going to put both sides to the base of 10, because 10 to the log base 10 will simplify out, leaving us with what's inside. So 2x times x minus 5 is equal to, well, 10 squared. We could rewrite it as 100, or we can leave it as 10 squared, because we still have some products, some simplifying to do before we fully start solving. Questions on how we got to 2x times x minus 5 equals 10 squared? Now at this point here, we do need to multiply out. On the left-hand side, we will distribute the 2x. 2x times x is 2x squared. 2x times negative 5 is going to be negative 10x. And 10 squared is 100. Now, unlike most of the problems we had on Thursday, we do have an x squared term. Because we have this x squared, this quadratic term, we do need to get this equation equal to 0. So the first thing I would do is subtract 100 from both sides. Because on the right-hand side, 100 minus 100 is indeed 0. 2x squared, negative 10x, and negative 100, none of those are like terms, which tells me that we have 2x squared minus 10x minus 100 is equal to 0. Questions on this here? Now, because we do have a quadratic equation, 2x squared minus 10x minus 100 equals 0, we need to solve this for x. Now, we can do it by factoring. And the first thing I see is that there is a greatest common factor between 2, 10, and 100, which is 2. And if we factor the 2 out of 2x squared, we're left with x squared. If I factor the 2 out of 10x, we're left with 5x. And if we factor the 2 out of 100, we're left with 50. Since we finished greatest common factor, we'll move on to our two sets of parentheses with 3 spaces. Then we find the sign. If the third term is positive, the signs are the same and match the sign of the middle term. If the third term is negative, which indeed it is, our signs are opposite. Factors of the first term, well, the only factors of x squared are x and x. Factors of the third term, factors of 50. 1 and 50. 2 and 25. 3 is not a factor of it. 4 is not, but we do have 5 and 10. And most likely we're going to want positive 5 and negative 10. And if I wanted to, I could check it off to the side. X times negative 10 is negative 10x. 5 times x is going to be positive 5x. Negative 10x plus 5x, negative 10 plus 5 does indeed give us the negative 5 middle term that we want. And the whole goal was to get it written in this product form, because whenever I have two or more things multiplied together to equal 0, one of those terms has to be 0. So we're saying that either x plus 5 is 0 or x minus 10. We don't care so much about the 2 because there's no way for me to make that 2, this 2 here, be 0. Nothing I can do to it. Now we're going to solve these here. Our x plus 5 we would subtract 5. Mm-hmm. Yeah. Yep. Yes. Yep. Got it.
Thank you, sir.
You're welcome. Now we're going to do the same thing on with the x minus 10, but this time we're going to add 10, telling us x is equal to 10. Questions on how we got these two solutions? Now with logarithms, we do have to be careful. So the two solutions we got were negative 5 and 10. Now we're going to want to check this. I'm going to check x equals 10 first, because we're saying log of 2 times 10 plus log of 10 minus 5 should equal 2. Now we can simplify this a little bit before we try to plug it in or do calculations, because inside the first log, 2 times 10 is 20. Inside our second log, 10 minus 5 is 5. Now this is fine because what we have, log of 20, log of 5, we're taking logarithms of positive numbers. And we can go log of, what was it? Yeah, log of 20 plus log of 5. And it does tell us it is indeed equal to 2. So we're good. 2 is equal to 2. Now we're going to do the exact same thing, but instead of checking it with 10, we're now going to check it with negative 5, because that was our other solution. Now inside the first log, 2 times negative 5 would be negative 10. Negative 5 minus 5 is also negative 10. I can grab the calculator and say log of negative 10 plus log of negative 10, and it tells us that the answer is domain error. Because we cannot take log of a negative number, it tells me that x is equal to negative 5. Does not work. It's an extraneous solution. And it's not so much due to the fact that x is equal to a negative number, but when we plugged it back into the original problem and simplified, we ended up with a negative number inside the logarithm. Questions on this here? We ready for the next one? Log base 6 of 6x plus log base 6 of x minus 1 equals 2. Focus up here. Now the first thing we need to do is rewrite this as a single logarithm. Since I have two logs with the same base being added together, we can rewrite it as a single log with what's inside those logarithms being multiplied together. So we'd have log base 6 of 6x times x minus 1. Now to get the variable out of the logarithm, we need to put both sides of this equation to the base of what? 6. Because our 6 to the log base 6, well, the 6 and log base 6 would cancel, leaving us with 6x times x minus 1 is equal to 6 squared. 6x times x is 6x squared. 6x times negative 1 is negative 6x. And 6 squared, 6 times 6 would give us 36. Again, just like the last one, we do have a quadratic term. We have that x squared term. So we need to get this equation equal to 0. Getting us to 6x squared minus 6x minus 36 is equal to 0. Yes? Kind of like the last one, there is a greatest common factor of 6, yes? Since we're solving, not factoring, because we're using factoring to solve, but our main goal is solving, did this 2 have any big impact on the solution? No. So is there anything saying that I can't just go, say here, divide everything by 2, thus removing this here? No. So here, having the fact that there is this greatest common factor of 6, it feels like I could just divide everything by 6. 6x squared divided by 6 is x squared. Negative 6x divided by 6 is negative x. Negative 36 divided by 6 is 6. And lastly, 0 divided by 6 is 0. And if we went and graphed both of these, 6x squared minus 6x minus 36 and x squared minus x minus 6, we get these two graphs, which 99% of their graphs are completely different, except for 2 points. And the only 2 points that are the exact same for this here is where it crosses the x-axis. The only thing that's the same for both graphs are the values of x that will make this function be 0. Because if we were actually wanting the function and factoring it, yes, we need that greatest common factor. Here, we don't care about what the factor is. We just want to know what value of x is going to make this function be 0. So I can divide that 6, that common factor, out of the entire equation, get rid of it, because it's not necessary for the solution. You cannot divide variables out. If you divide a variable out, even though it's in common, you're removing a solution. But that also means, because this looks like nice intersections, we can go second graph. And the graphing calculator tells us that this function is 0 at negative 2 and 3. So our two solutions are negative 2 and 3. All right. But before we can say we're done, it is going to be helpful to check negative 2 and 3. Most likely, negative 2 is not going to work because there's nothing in either one of these to offset that negative sign. So if I check log base 2 of 6, log base 6 of 6 times negative 2 plus log base 6 of negative 2 minus 1, well, 6 times negative 2 is negative 12. And really, at this point, we can just exclude negative 2. Because that logarithm, as simplified as it gets, I'm taking log of a negative number. It does not work. If we looked at the other one, negative 2 minus 1 is negative 3. Okay, yeah, negative 2 is out completely. Now we can do the same thing with 3. all these values are going to change. Six times 3 is 18. 3 minus 1 is 2. We can grab the graphing calculator and say math. Log base 6, log base 6 of 18 plus log base 6 of 2 is indeed 2, telling us 2 is equal to 2. So the only solution that worked for this here was positive 3. Not always going to necessarily be that the positive value works, but in the main ones we've done so far, that's how that's worked out. Questions on these so far? We ready for the next one? Do we want to look at problem number 7 or problem number 8? Okay. We'll look at problem number 8. Log base 4 of x plus 12 plus log base 4 of x equals 3. Again, I have two logs with the same base being added together, so we can rewrite it as a single log with what's inside being multiplied. Now, yes, if I wanted to, I could have rewrote it as x times x plus 12 inside the parentheses. Product doesn't matter. But we now have one term on both sides, so we can put both sides to the base of 4. 4 to the log base 4 will simplify, leaving us with x times x plus 12 is equal to 4 to the third. Now the left-hand side's kind of nice. We just need to distribute the x. X times x is x squared. X times 12 is 12x. Now 4 to the third, we can check to see if it is a nice number. 4 to the third is 64. Now we just need to get this equation equal to 0 because we have that x squared term. Not only that, but we do have a middle term, telling us that x squared plus 12x minus 64 is equal to 0. Questions on how we got to this point here? There is no term in front of x squared, so do we want to factor it or graph it? So we can factor. Since the third term is negative, the signs are opposite. Factors of x squared are only one set, x and x. Factors of 64 are 1 and 64, 2 and 32. 3 doesn't work. 4 and 16. 5 doesn't work. 6 doesn't work. 8 and 8. I wouldn't pick 8 and 8 because that'd make the middle term 0. So you probably want 16 and 4. Two expressions multiplied together to equal 0. One of those is going to have to be 0. X plus 16, we would subtract 16 from both sides, telling us x is equal to negative 16. With our x minus 4, we would add 4 to both sides, telling us x is equal to 4. So we get negative 16 and 4. Most likely, which one's not going to work? The negative 16. That second one really tells us it's not going to work. Because we'd have log base 4, a negative 16 plus 12, plus log base 4 of Yeah, log base 4 negative 16 is not going to work. But if we simplified it all the way down before calculating, do anything with it, yeah, log base 4 of negative 4 we cannot have. We cannot actually get that. Neither can we use or evaluate log base 4 of negative 16. Don't work. That leaves us with 4. 4 plus 12 is 16. And that's just 4. Well, log base 4 of 4, since the base and what's inside it are the same, it would be 1. Log base 4 of 16 is also nice. 4 to what power is 16? Well, that would be 2. 1 plus 2 is indeed 3. So as we suspected, x equals negative 16 is thrown out. X equals 4 is our only solution. Questions on this here? Questions on any of this so far? Now, we're going to skip all the way to this one, because I want to make sure we hit this one first. If we have time, we'll go back to the subtraction ones, but I do want to make sure we hit this one first. Now, for the most part, most of the steps are going to be the exact same. I do have two natural logs being added together. I want to rewrite it as a single log with what's inside being multiplied together. Nothing's changed there. The next main step, I need to get the variable out of the log, so I need to put both sides to the base of what the base of the log is, which would be what? E. Again, no real difference. E to the natural log. E in the natural log will simplify, leaving us with x times x minus 5 equals e to the third. Again, nothing's changed. Nothing's really different than what we've been doing. Left side will distribute the x. X times x is x squared. X times negative 5 is negative 5x. E to the third. Well, grab the calculator. Second ln. Third is 20.08553692. And it continues on as a non-repeating, non-terminating decimal. Now there might be some out there that say we're going to just approximate E at this point to 20.0855. I would say no, because this is way too early in the problem to round. Because if we round now, there's a good chance we're going to have to round later. I don't want to round twice in the same problem. So we're just going to leave it as e to the third power. We do have quadratic terms, so that means we can get this. We need to get this equal to 0. Telling me that x squared minus 5x minus e to the third is equal to 0. Questions on this here? Now, factoring is not going to be nice because we do have irrational numbers. So we're going to have to go back to a method that worked every single time. Not b squared. A quadratic formula. X is equal to negative e plus or minus the square root of b squared minus 4ac all over 2a. And again, this worked with our quadratic equation, ax squared plus bx plus c. A is the number in front of x squared. In this case would be 1, because there's not one written. B would be the number in front of x, which is negative 5. And c would be what? Almost. Negative e cubed, because we have the sign in front of it. Minus e cubed, so it's negative e cubed. Now, it seems it's odd that we can do this, but remember, e is just a number. It's just taking the place of that number. It's an irrational number, but it still works. So now we can start plugging this back in. So negative b would be negative negative 5, plus or minus the square root of negative 5 squared minus 4 times our a, which is 1, times c, which is negative e to the third, all over 2 times a, 2 times 1. Questions on how we plugged any of this in? Negative negative 5, which is going to be 5. On bottom, 2 times 1 is 2. Now, normally, at this point here, we'd plug everything inside the radical in the calculator and let it do it for us, or simplify it for us. But unfortunately, e cubed, it being an irrational number, is going to turn that whole thing into a decimal. So instead of doing that, we're going to simplify the two parts. Negative 5 squared, well, negative 5 times negative 5 is 25. Negative, and then minus 4 times 1 times negative e cubed. Well, our negative 4 times 1 is negative 4. Our negative 4 times negative e to the third, well, that negative and negative would make a positive. 4 times e to the third is just going to be 4e cubed. So x is equal to 5 plus or minus 20, square root of 25 plus 4e cubed all over 2. So we'd had to have approximated, because if I approximated that e value earlier, I'm definitely going to have to approximate the square root of that approximation. Now, because of the plus or minus, there are actually two solutions here. Not 4. Because we have the plus and we have the minus. Now, if this had been just a quadratic equation, we would have taken this here and say we're all good. But because this value of x is going inside of a logarithm, if either one of these values made the expression inside the logarithm be negative, we have to throw it out. Now the question is, how do we figure this out? Yes? I just grabbed the calculator because it's 5 plus second square root 25 plus 4. Second ln gives us e cubed all over 2. So one of the values is approximately 7.632. Now we can go do this again. 5 minus this time square root 25 plus 4 e cubed all over 2. Negative 2.632. Now we just need to check it. Well, negative 2.632 is probably going to be the one we're going to throw out. And that is the case. Because we would be natural log negative 2.632 plus the natural log of, that's what I did, negative 2.632 minus 5. I don't know why. But during the first hour, I wrote plus instead of minus. Didn't change anything. But if we simplify, we get natural log of negative 2.632 plus the natural log of negative 7.632. I can't take the natural log of a negative number, so we throw it out. 7.632. Both are positive. 7.632. And it should come out close to 3. It's not going to be exactly 3 because we approximated, but it is close enough. And when I say close enough, we rounded to 3 decimal places. It's beyond 3. That's not a solid rule, but it does kind of work. This is what we get. Questions on this here? Now, we'll go back to this one. You won't normally see this. You won't normally come across it, but it is possible to start out with 2 logarithms being subtracted. Because our quotient property says if I have 2 logs being subtracted, I can rewrite this as a single log with what's inside being divided. Because the big thing with this is not so much how it's set up, it's getting it to 1 log. I want 1 log or 1 term on both sides. 1 expression. Now we'll do the exact same thing. We're going to put both sides to the base of 10. Telling me that 3x minus 2 over 2 is equal to 10 to the third, or 1,000. Solve for x. First thing I do is multiply by 2 to get rid of that division. Tell me that 3x minus 2 is equal to 2,000. Then we would add 2 to both sides. That's it. Positive number, we could plug it in and check, but realistically, the process doesn't change. We have to write it as a quotient, do the same stuff. That's it.